Suppose we're trying to find the region of this area here that's enclosed by the x-axis, the y-axis, which is x equals 0, the vertical line x equals 6. Up top, it's enclosed by the function y equals x squared plus 1. Well, we don't have a basic geometric shape. That's not any particular shape to use. So here our idea is let's use something we know. We're going to divide this region into some number of rectangles. We'll let n equal the number of rectangles that we're going to divide this region up into. Now, the width of each rectangle, we can make really anything we want, but typically we make them all the same width. Okay, so let's suppose in this case that we're going to use 3 rectangles. And if we want them to all have the same width, and because the width is along the x-axis here, then it's typically called delta for change in x, or some amount of x. And if they're going to be the same in their width, well, we take the 6 minus the 0, because that's the total, and divide it by the number of equal parts we want. Each rectangle should have a width of 2. Okay, so our first guy is going to stretch from x equals 0 over here to x equals 2. Our next one will go from 2 to 4. And our last rectangle will go from 4 to 6. So what we're saying is that each of our rectangles, and we don't see any rectangles over in this big picture yet, but each of our rectangles will have a width of 2. The height that we're going to use for each rectangle is going to be some value of the function, because this height is bounded by x squared plus 1. So we're going to be using our height, that's our width of 2, our height will be f of x for some value of x that we get to choose. Well, there are 2 really common choices that are made in problems like this. And that is either we're going to use the left endpoint of each interval, which in our case, our first interval 0 to 2 would have a left endpoint at 0. Our second interval, 2 to 4, would have a left endpoint at 2. And our third interval, that goes from 4 to 6, has a left endpoint at 4. So if we're going to do a left endpoint sum, and this particular type of sum is called a Riemann sum, when we're trying to approximate the area under that curve, then we need to know what is the function's value at 0, because that's going to be the height of our first rectangle. If I insert this rectangle into our picture here, then it looks something like this. I'll shade it in real dark. That's our first rectangle right there. It's going to use the function's height at 0, which is f of 0, for the height of the rectangle. Okay, well, f of 0, since it's x squared plus 1, is simply 0 squared plus 1, which is 1. The height of our second rectangle, I'll insert the point 0, 1 there so you can see that. The height of our second rectangle, well, it stretches from 2 to 4. And if I'm going to use the left endpoint of the interval, it would be 2 for the height. Then in the picture, it looks like this. Shade him in real dark. Okay. Now, f of 2, the function's value at 2, is 2 squared plus 1, that's 5. Okay, here's this point that I'm using for the height here. That's the point, the y value of that point is 5. Okay, my third rectangle, stretches from x equals 4 to x equals 6. Okay, well, I'm going to use the value of 4. So my third rectangle looks like this. Those widths are all supposed to be equal. Okay, so this is my third rectangle. Okay. Its height is the function's value at 4. Well, f of 4 is 4 squared plus 1, which is 17. Okay, well, that means my left endpoint sum is simply the width 2, that's my first rectangle, times the height of 1. That's this rectangle here that stretches from 0 to 2 and has a height of 1. Our next rectangle, so this is rectangle, let's go R1. Okay, our next rectangle again has a width of 2, but its height was 5 because that's the function's value there at 2 was 5. Okay, and our third rectangle has a function's value, has again a width of 2, so here's R2 on this guy, has a width of 2, but its height is 4 squared plus 1. Let's put that up here. That's the point 4, and the 17 is the height of that third rectangle. So 2 times 17. So if we carry this out, our left endpoint Riemann sum, which is our approximate value of the area under the curve, is 2 plus 10 plus 34, 2 plus 10 plus 34, and that looks like it must be 46 square units. Okay, now if we're just calling it a Riemann sum, we'll leave the units off, but in this case we're talking area, so we can leave it on. Either way is fine. Now let's suppose instead of doing a left endpoint sum, and notice what happens before we get there with this left endpoint sum. The rectangles don't quite come up to the curve, so this area here that's lighter, that's error. This is error up here, and this is error up here, that we've underestimated the area under the curve. Okay, but it is an estimate of the area under the curve. Okay, we could also do a right endpoint Riemann sum. Typically, the problem will tell you which one to do. Well, what that means is, rather than using the function's value at the left endpoints, 0, 2, and 4, we'll use the function's value at the right endpoints of each interval, 2, 4, and 6, to get the height of the 3 rectangles. So that means my first rectangle is actually going to be taller than it used to be. It's going to stretch all the way up here to y equals 5. Our second rectangle is going to stretch all the way up here to y equals 17. Notice these rectangles lie above our curve x squared plus 1. And we've already calculated those y values there. The last rectangle, I have to calculate this value, and that just comes from f of 6. F of 6 is 6 squared plus 1 is 37. So this is the point 6, 37, way up there. All right, so my right endpoint Riemann sum, well, it's going to be the same 2 times 5. That's this first rectangle here. Using the right endpoint of my second, that is at 17, same 17 that we used down here. So this will be 2 times 17. And my third rectangle now stretches all the way up to y value of 37. So 2 times 37. Okay, and that is 10 plus 34 plus 74. Okay, this is 44 and 74 looks like 118 square units. Okay, well, the right endpoint Riemann sum over approximates the area under the curve. It's way too big. And the left endpoint Riemann sum was way too small. The truth lies somewhere in between. Now, what would give you the exact area? Well, now that you know about integrals, the area under f of x equals x squared plus 1 from x equals 0 to x equals 6 is given by the definite integral. The integral from 0 to 6 of x squared plus 1 with respect to x gives us our answer. And you know now that this is x cubed over 3 plus x evaluated at 6 and at 0, which is 6 cubed over 3 plus 6 minus 0 cubed over 3 plus 0. And this number works out to be 216 over 3 is 72 plus 6 is 78 minus 0 is 78. So now that we know about integrals, this problem can be phrased in a couple of ways. We can say that we are approximating the area under f of x equals x squared plus 1, either using a left endpoint Riemann sum with, in this case, 3 rectangles, or a right endpoint Riemann sum using 3 rectangles. And we can see we got much different answers, 46 and 118, or we can do this and get the true area. So sometimes we phrase this question as approximate the integral using a Riemann sum. Sometimes we phrase it as approximating the area under the curve using a Riemann sum.